We're going to tackle a question today that seems, well, pretty simple on the surface, but it's a question that's stumped brilliant minds for centuries. How do you measure something that's constantly changing, but at one single frozen instant? The answer? It's a powerful idea called the derivative. And believe me, it is the key to understanding our world in motion. Okay, so let's just dive right in with a question that sounds easy, but is actually surprisingly tricky. Picture a car moving down the road. Calculating its average speed is no problem, right? But what if I asked you, how fast is it going at the exact instant it passes that streetlight? Not over the course of a second, but in a single frozen moment in time. How would you even begin to measure? And this is where we hit a wall. Average speed, that's easy. It's just the total distance you traveled divided by the total time it took. Simple. But for instantaneous speed, the time interval is, well, it's zero. And as you probably remember from math class, dividing by zero, you just can't do it. It's a mathematical no-go. And fun fact, this exact puzzle is what pushed people to invent calculus in the first place. Yeah, at first glance, trying to measure something over zero time feels, well, impossible. But it's this very challenge that forces us to get clever and develop a totally new way of thinking about change itself. So the real concept we're chasing here has a name. It's the instantaneous rate of change. And to really get a grip on this, let's turn it into a picture. We can actually plot that car's whole journey on a graph, right? We'll put time on the bottom axis and the distance it's traveled on the vertical one. Now, on this graph, we can show the average speed between any two moments in time with something called a secant line. You just draw a straight line connecting those 2 points on the curve. The slope of that line, rise over run, is literally the change in distance over the change in time. And that right there is our average speed. Pretty straightforward. But remember, we don't want the average speed between 2 points. We want the speed at one single point. So what do? If we can't measure it directly, what if we could kind of sneak up on the answer? And here comes the big idea, the key insight. Let's take those 2 points that define our secant line and just start sliding them closer and closer together on the curve. As they get closer, watch what happens to the line. It pivots, and its slope gets better and better. It becomes a much closer approximation of the speed at that one instant we're targeting, and we can make this gap between them ridiculously small. A tenth of a second? A thousandth? How about a millionth of a second? As that time interval shrinks and shrinks, the slope of our secant line starts to zero in on one very specific single value. And this leads us right to the aha moment. What actually happens when we take this whole shrinking process to its absolute logical extreme? This is it. This is the whole ball game. What happens in the limit as those 2 points basically merge into one? That secant line, it has to become something else, something new. And here's where the magic is. If you could zoom in infinitely close on any smooth curve, it would start to look like a perfectly straight line. So our secant line, which used to cut through 2 different points, finally settles into this perfect position where it just kisses the curve at that one single point, matching its slope perfectly. We call this new line the tangent line, and its slope, it's not an approximation anymore. It is the exact, precise, instantaneous rate of change at that one point. We did it! We solved the puzzle. So we've actually found our answer, and this incredibly powerful idea, the slope of the tangent line, it has a formal name, and it's the absolute star of our show today. It's called the derivative. Simple as that. The derivative of a function at a specific point is the instantaneous rate of change at that point. In fact, it's a whole new function that can tell us the slope or the rate of change of our original function at every single point along the way. Okay, I know what you're thinking. A big, scary formula, right? But don't let it intimidate you, because it's just the fancy mathematical way of writing down what we literally just did visually. This part, f of x plus h minus f of x, that's just the change in distance, our rise. And h, that's just the tiny change in time, our run. And this lim h goes to 0 part simply means, let's see what happens as that time interval, h, shrinks down to 0. That's it. It's the slope of the secant line, taken to its absolute limit. Now, there is one important catch. For a derivative to even exist at a point, the function has to be smooth there. If you have a sharp corner, a kink, like the one on the absolute value graph right at 0, well, you can't really define a single tangent line, can you? The direction changes so abruptly, the derivative just doesn't exist at that one spot. So the big question is, why does this one idea matter so much? Why is it so revolutionary? Well, because once you can measure instantaneous change, you can precisely describe a world that is constantly, always in motion. I mean, this is just beautiful. Think about it. If you have a function that describes an object's position over time, its derivative gives you its velocity. That's the instantaneous rate of change of position. Then if you take the derivative of that function, you get its acceleration, the rate of change of velocity. It's incredible. And its power goes way, way beyond just physics. In economics, it's used to find the marginal cost, the cost of producing just one more item. In computer science, it is the absolute heart of how machine learning algorithms learn. In biology, it's used to model how populations grow. Seriously, it is everywhere. So you see, the derivative is so much more than just a formula in a math book. It's a lens. It's a fundamental way of looking at the universe. It gives us this incredible power to look at anything that's in flux, from a growing economy to a speeding rocket, and ask the ultimate question: how is it changing right now? And being able to answer that, well, that is a truly powerful idea.